My name is Duncan Platt, and I work at RISE Research Institute of Sweden. RISE, of course, is one of the partners within Treesearch, so I won't spend much time, but just to say we are Sweden's research institute. We are owned by the Swedish government and report to the Department of Industry. We're roughly 3,000 employees at RISE, and RISE is quite new on the landscape in Sweden. Since 2016, there's been an integration of roughly 36 smaller institutes that have been gradually merged and integrated together to form RISE Research Institute of Sweden. I'm situated in Norrköping, and oops, I'm sorry, I'm not being able to advance my, there we go. I'm situated in Norrköping, and where the printed electronics arena is, which we will be talking about today. But just to say that RISE is a very broad institute, so perhaps you have other interests and maybe need help. So RISE is working and in strong collaboration with both academy and the public sector and the industry in Sweden to help with the global challenges, sustainability and more. Within the ranges you can see here for everything from AI and data science to energy or transportation, digitalization and so on. But really, what I was really wanting to say is that there are a number of test and demonstration facilities. So RISE, the whole of RISE, it's from the north of Sweden, where Mikael is sitting in Luleå, all the way down to Malmö and east to west as well. But one of the strong functions of RISE, where we collaborate with many, is running or administrating test and demonstration facilities, which can be different sorts of test beds. It can be, for example, semiconductor processing, or it can be fiber optics. It can be within the, if you like, IT sector for cybersecurity, the cyber range, or it can be for innovation, dynamic test beds as well, or user experience. So just mention that. So it's over 130 test beds that RISE operates in different parts of Sweden. And we'll be talking about printed electronics arena today. Very briefly then, to introduce this, printed electronics arena is an innovation cluster. It's also known as the Swedish Laboratory for Research in Printed Electronics. It's has different financiers. A lot of the equipment has been purchased via the Knut and Alice Wallenberg Foundation through grants there, and also a lot of the operations have been financed by Vinnova and the Smart Electronic System Strategic Innovation Program. And you can see in the picture, the top right, that is the campus Norrköping of Linköping University, where Christine and other of the fantastic researchers at the Laboratory of Organic Electronics sit. And if you go across the bridge that you see in that picture, you come to the other side and you see the printed electronics arena, which is the sort of red brick building that you can see in the picture down to the right. And we also have support, of course, from the local council, Norrköping Council, in the local region in Östergötland. Also very briefly, just to see how we fit in, how printed electronics arena fits in. It's an open innovation cluster and research laboratory, working with everything from, how would you say, fundamental research to high level, high TRL, pilot line, to support industry as well. We work in close collaboration with the Laboratory of Organic Electronics, of course, here in Norrköping, led by Professor Magnus Berggren, and we RISE, Printed Electronics Arena. Also, of course, Treesearch, but also RISE is hosting, in close collaboration, of course, with many of the partners in Treesearch, the Digital Cellulose Center. And we also collaborate closely with the Innovative Materials Arena in Linköping. And for the sort of commercial activities, we have the LiU Innovation helping together with the science parks and incubators to form the local ecosystem. And as a final comment, there's a newly forming home of organic and printed electronics, which is, if you like, a company accelerator, which is in the formation to take care of the spin-off companies or the growth companies within the printed and organic electronics area. So that's just a little brief on the ecosystem. So this will be a very, very short crash course on printed and organic electronics. Many of you are more expert than me, I believe, but anyway, just very briefly, printed electronics, where we are working, at least at the printed electronics arena, is very much like the technology you would use at the graphical printers, or even the sort of printing technology that you would use to put, say, icons or patterns on textiles or on newspapers or magazines, whatever it could be. You can see the screen printing in the little graphic in the middle on the left-hand side. You have a filler and a squeegee, where the filler, if you like, spreads the ink over a mask, and then the squeegee pushes the ink down through the mask so that you leave a pattern onto the substrate that you are printing. You can also use inkjet printing, which is the same technique that you might have in your desktop printers, where ink drops are pressed out, if you like, using a piezo actuator to put an ink drop on a substrate or a paper, or whatever it might be. The trick is, of course, the advanced functional materials that you want to print. These can be conductors, carbon-based, or metals, semiconductors, primarily organic, that our activities are working with, insulators, electrolytes, sensor materials, display materials, and encapsulation materials. So a lot of the, how would you say, the skill and research is in producing stable inks that can be printed and are stable with time, and also after curing, overprintable, so that you can create stacks of different functional materials to create electronic circuitry, if you like. Printed electronics, of course, it has its limitations, and sometimes if you need advanced functioning or wireless communication, which can't be achieved today with 100% printed solutions, then you may need what we call a hybrid system, where we combine conventional components with printed electronics to create a hybrid printed electronic system. So examples of what you can do, very briefly, you can make organic electrochemical transistors, which can be equivalent to P-type depletion mode transistors. And new research at the Laboratory of Organic Electronics has now developed N-type complementary organic electrochemical transistors, with even a spin-off called N-ink. And so transistors, sensor materials can be printed, or you can use materials to create sensors, electrochromic displays, and even electroluminescent displays can be printed. Antennas, if you like, for the wireless communication, using metallic inks, for example, silver, or even at very close range, carbon-based inks. Energy storage, of course, for making, for example, IoT sensors. You may want to store energy. You can have organic batteries, organic supercapacitors. You may want to do energy conversion, heating to cooling, or harvesting energy through the thermoelectric effect. Photovoltaics, organic, radio frequency harvesting as well, all give opportunities for printed solutions to capture and use, store energy in different solutions. The potential advantages, these solutions and substrates, they can be light, thin, flexible, soft, stretchable, apologies for the spelling, and sustainable. So it gives many opportunities for packaging in novel ways. And if you can develop inks that are also stretchable, then you can even have stretchable solutions, which could be, for example, integrated in textiles, or can be directly printed on the body, for example. If you're working with organic and bio materials, biocompatible materials, then it opens up possibilities for having, if you like, printable solutions and the interface to the body, or even within the body. Of course, a lot of the research is in the area of sensors, where one of the many applications for printed electronics and organic electronics can be. You can print on a large area, so it's possible to do high volume sensor production. But if you combine it with displays or energy harvesting, then you can have a very potentially low cost, high volume sensor solution, which could be used, for example, in the tracking of vaccines for cold chain indicator, or other possibilities. You can also print, for example, piezoelectric materials such as PVDF, and you could integrate that, for example, in a smart sock, which could be used for measuring temperature and pressure, which could be used in the diagnosis, early diagnosis of diabetes, for example, in elderly patients. Electrochromic displays is another key area for printed and organic electronics. Here you can see an organic electrochromic display. Here we even have colored electrochromic displays as well, which can be activated at low voltages, so only 1.5 volts is necessary. So this technology is actually, depending on how often you activate or deactivate your display, is more energy efficient than e-ink or e-paper. So it is actually, in certain situations, the lowest energy consuming display technology, but it's a purely reflective display. It's not an emissive display. Also, regarding component integration, printed electronics transistors can't compete, for example, with Intel with 4 nanometer gates, but the gate size for the screen printed transistors are roughly 140 micrometers, and this can be integrated to create, for example, decoders or 7-segment displays. And you could say that this kind of level of logic is somewhere where you would be at the end of the 60s or early 70s for the PMOS logic, but of course big advancements are being made using the OACT N-type ink, which is going to accelerate this progression. And the printed electronics arena, with the strong collaboration with LiU and RISE, published at the 2020, and the picture down to the left, which was the state of the art for large scale integration of screen printed electrochromic solutions. So it was the large scale integration state of the art at that time. So very, very brief on that, but just to get deeper into the capabilities at the printed electronics arena, which I think is the main interest today for everybody. I won't go through all the list, but the personnel, of course, in strong collaboration between Linköping University and RISE at PIA, can help with the development of printing and patterning processes and device design, formulations, even integration, hybrid developments, rapid prototyping, all the way up to pilot production and proof of concept prototype series. Also kind of support with the printing, drying, curing processes, which are required to make the prints stable and then overprintable. Also working with the materials and ink formulation. So I'll just go a little bit deeper into those. Can you hear the sound?
No.
Okay. Oh, well, I'll just, this is just showing the screen printing lab here. This is inside the deck screen printer machine, and you put the ink on top of the mesh, and then the filler comes down and provides a very good even pressure to spread the ink evenly over the mask and the mesh. So you can just see that process. So this is our deck printer, and then the squeegee comes down and pushes the ink down through the mesh in the mask, so that you get a very even screen printing. So we have two of these deck machines inside the printed electronics arena. We also have a fully automated sheet-based screen printing machine called the Atma, which can produce roughly 250 sheets of printed A4 sheets an hour. We have also an IACRA E2 screen and stencil printing machine. So these are all excellent possibilities. The deck machine itself has a resolution roughly 25 to 50 micrometers accuracy. It's semi-automatic. The Atma fully automatic is roughly 100 to 200 micrometers in the resolution. And to perform the drying and curing, then we have you saw in the film very briefly, a NatGraph machine, which is an Air Force combi dryer, which can use hot air, infrared, or UV to do the curing of the inks in the line. Not very often used, but you also have a Testacolor gravure and flexo printing station machine as well. Also getting to inkjet printing, we through the Wallenberg Foundation at Printed Electronics Arena, there is a Ceradrop F series, very advanced inkjet printing machine, which in conjunction has an aerosol module as well, Opto, right? So you can do both inkjet printing or aerosol jet printing using that machine. You can see a little bit in the, how would you say, in the graphics here, they show you a little bit how that is. The resolution using the aerosol is even finer than the inkjet, so you can get down to better than 10 micrometers printing accuracy. For lab work as well, there is a Dymatics. You can down on the bottom left picture. That's also a cartridge based inkjet printer. Not as advanced as Ceradrop, but it certainly is good for many applications. There, the maximum you can have standard Fuji film cartridges where you have 16 nozzles. Whereas using the Ceradrop, you can have very advanced cartridges up to 1,028 nozzles in each cartridge. They can dispense accuracies at around about 1 picoliter to 10 picoliter, depending on the different types of cartridges being used. Also moving towards deposition or scaling up, there is a slot die coater at Printed Electronics Arena as well. And we're also building from scratch a reel-to-reel large area inkjet printer at the moment, which we hope to be able to offer at some time during the coming year. So. Oops. My computer crashed. Can you still see?
Nope.
Let me stop sharing. I just had a crash there. Apologies. Let me share again. That was unfortunate.
No worries. We still have a little bit of time. So in the meantime, you guys can think about the questions and you can start posting them in the chat and in the Q&A or raising your hands, and then we will take your questions after Duncan finishes his presentation.
I'm sorry, it's hung my computer. Give me a few seconds. I apologize profusely. And it's
no worries. And I think that, yes, overall, it was really great for me also to see your presentation. Yes, it's really insightful.
I'll be back soon. Let me see. Let's see if I can share again. So I just have to get back to the pages again, sorry.
So if you guys want to apply and get access to this particular infrastructure, you just need to go to the Treesearch webpage, and then in the infrastructure page, you select the Linköping University. And currently we call this lab a Swedish Research Laboratory for Printed Electronics. But we will see, maybe we should rename it to the Printed Electronics Arena. So I will discuss it with.
Yeah, it is. It has both names. It's how would you say? It has two names. So let me see here. Let's see if I'm back online here now properly with the. Can you see the presentation again?
Yes, works very well.
I think the video somehow caused everything to hang there. Sorry. So yeah, also for making hybrid, we have again through the Wallenberg Foundation, there is an advanced pick and place machine, so it's possible to assemble bare dies, for example, on cellulose substrates, if that's of interest for Treesearch. We can do laser cutting and engraving. You can see also again in the graphics, it's possible to engrave and lift off, if you like, different patterns or printed solutions that you might want to work with. And there is a spin-off called dry face patterning. You can see there the process. You are instead of using etching to create a PCB, you can use a foil and mechanically, if you like, you physically remove the to create the pattern that you're after. So you can create a one-layer PCB, which would be excellent, for example, for RFID or other solutions where you are looking to make higher volumes. And this removes entirely the chemical from the production process, chemical etching, for example. So these possibilities exist. We can do rapid prototyping as well. We have a PCB milling machine, and we have 3D printers available there. So 3 different ones, a Formlabs, which is a bit more advanced, and a Prusa and Creality 3D printers there available at PIA. And also for the ink and adhesive developments, there's how would you say, powder milling machines and rheometers for characterization. There's the possibility to do high shear mixing, speed mixing, and there's probe sonicators. So it gives you the what you do require for making the ink formulations and also for analyzing them. Also for analysis, there's a lot of electrical equipment or analysis equipment in the lab, but perhaps one of the most used and very important ones for characterizing, for example, transistors is the full parameter analyzer from Keithley, which is also available at the Printed Electronics Arena. And where to find the information? Obviously, this is very brief, but you're welcome to contact myself, of course, or through the Treesearch team. But you can find information on www.printedelectronicsarena.com. And if you see down to the icon on the bottom right, there is actually a virtual tour that you can go into that will guide you there. So it sort of takes you to the entry of the Printed Electronics Arena. It's a bit like, if you like Google Maps, you can just go in and go through the lab, or you can stop at the different information points, and that'll tell you a bit more about the different machineries and equipments that are there. So you're very welcome to follow that and discover more about the Printed Electronics Arena or the Swedish Laboratory for Research in Printed Electronics. That's really the slides I was going to present, but you're very welcome to Printed Electronics Arena. Hopefully bookable through LIMS in not too distant future, and we look forward to sort of collaborating and welcoming. And just to show very, very quickly the kind of things that can be done using printed electronics. Many of you know this. For example, we can use the body fluid as the electrolyte, if you like, in making self-powered, battery-free, chip-free indicators for highly absorbent bandages. The company Absabest is launching that product just now. You could have temperature labels for cold chain monitoring using hybrid printed electronics. You can print bare dies, as I was mentioning, on top of cellulose substrates using the pick and place machine as a part of a hybrid system. This chip has a potential 6-port potentiostat, so it actually works to detect drugs of abuse, and the long-term hope is that that could be used as a sort of police control aid for discovering drugs of abuse. 10% of deaths in traffic are supposed to be related to narcotics abuse, so this could be very useful for the future. And being made out of how you say, forest-based materials, it becomes a very sustainable solution with just one chip mounted on top. I don't have time to talk deeply, but also energy. There's a spin-off called Lignin Energy, working, of course, with forest-based materials to create a battery. That's very sustainable battery technology. You can see principles also here in the film here, which shows how you could, in this case, they're supercapacitors, but you could fold these supercapacitors and put them into a pack based on built on organic forest-based materials, which can then be combined into larger battery packs. And again, can be used for sustainable solutions and built up and gradually to even larger, as the vision is for the future, very large battery powered systems based purely on forest-based materials. There's the company Invisible, which is working with or licensing the electrochromic display technology from the research from Linköping University and RISE, which is very exciting. Hopefully seeing something coming to the market. And as I mentioned, the spin-off company Dry Phase Patterning, who can help with creating these roll-to-roll substrates, as you can see an RFID example down in the corner. So I think I'll stop there just to give a taste. I hope that's okay for everyone.